Hi everyone, welcome to this lecture. So this lecture is all about polynomial regression. So what is happening till now is that we are trying to fit a straight line on every kind of data. So what if we try another shape rather than a straight line? Suppose we try to fit a sine wave on our data set, or we try to fit a curve on our data set. So that attempt is called polynomial regression. So here is the example of a polynomial regression. We can see our data set in blue color. So we are trying to fit a straight line, which is not a good fit for this kind of data set. We can see that here the points are spread. So we need another shape of regression rather than a straight line regression. So we need to fit a model that is other than a straight line model. So here we are trying to fit a straight line model on this data set, and this is the equation of a straight line model. So if we see this equation in terms of a polynomial regression, so here the degree of the polynomial is 1. The straight line is also a polynomial with degree 1 because the power or the exponent of our feature is 1 here. So when we have one exponent on our feature, so that is called a 1-degree polynomial, which is a straight line. But definitely here we need to increase the degree of polynomial because we can see that this straight line is not a best fit for this kind of data set. So here is another solution. Here we can see that we are trying to fit a shape in the form of a curve, or this is nearly a sine wave shape on our data set. We can see that this is a better fit as compared to fitting a straight line on this kind of data set. But here we can see the equation. Here the degree of polynomial is 3. Here you have to square your feature and you have to cube your feature, or you have to raise the power of your feature to 3. So this equation is representing this green curve or this green polynomial. So basically this is the advantage of polynomial regression. On one side, we are able to fit the curve or fit the regression model, which is other than a straight line. But on the other hand, if we see our regression equation, it becomes complex and complex. So this is the example of a 3-degree polynomial. So in general, if we have m order of a polynomial or m degree polynomial, so this is the general equation of a polynomial regression with m degree. So we can see that we have a weight associated with the first degree, we have another weight associated with the second degree term, and we have another weight associated with the third degree term. So if we have m degree equation, we need m weights, that is from W1 to Wm. So this is the equation of polynomial regression where we use mth order polynomial. So this is the form of the feature matrix. So if we want to construct our feature matrix for mth order polynomial, so the first column is always a 1. Then we have a features with 1 degree. Then we have features with 2 degree. Then we have features with 3 degree. And at the last, we have the column with the features of m degree, because this is an equation for m order polynomial. So we can see that our feature matrix will become complex as the degree of polynomial increases. So for m is equals to 3, this is the shape of our feature matrix. So if we want to implement the polynomial regression with 3-degree polynomial, so this is the equation, or this is the matrix of our feature. So we can see that the first column is a 1, then we have a features of first degree, then we have a second degree features, and we have a third degree feature because the order is 3 here. So here are the few examples of different order of polynomial regression. We can see that here m is equals to 0. That is, we are trying to fit this red line whose slope is 0. Here m is equals to 1. Again, we are fitting, or we are trying to fit a straight line on this data set, but here the slope is equals to 1. This is called the first degree polynomial. Here the degree of polynomial is 3, and we can see that this is our red line. The green line in each figure indicates that this is the best fit. So we can see that when m is equals to 3, we get the best fit on this data set. So here the red line shows the polynomial of 3 degree. Here we have the polynomial of 9th degree. So what is the difference between here? Here we can see that in the red color, we can see that this regression or this polynomial regression of 9th degree is trying very hard to touch every point. In this case, it is getting into an overfit stage, which we will study after few lectures. So this is the best fit. We do not need to touch every point, and in that attempt, we can see the shape of the polynomial becomes very, very complex, and its degree becomes so high that it is not easy to implement. So this is our best model with 3-degree polynomial. So in this lecture, we learn about the polynomial regression. We see that if a line is not a good fit for a training data, we can use another shape than a line. That is, we can use a curve or we can use a sine wave. In that case, our equation will become complex. There will be square, cube, and other higher powers on our feature. But on the other hand, we will get a good fit for our model. So in this lecture, we learn about the polynomial regression. We see the equation of the polynomial regression for m degree and for 3rd degree. So I hope you understood the concept of a polynomial regression. Thanks for listening, and I will see you in the next lecture where we will implement polynomial regression in Python.